So today we're going to talk about uniform circular motion, and we're going to, we'll define what uniform circular motion is, we'll review the definition of acceleration, and then we'll define an equation, or come up with an equation for what we call centripetal acceleration, and then we'll talk about centripetal force. Okay, so uniform circular motion. What does it mean? It means an object is moving in a circle. And they're just going in a circle, around and around and around and around and around and around. Now, the circle has a certain radius r. It's moving in a circle. And here we see a velocity vector v. So here's the object. Maybe it's like an object on a string or something, and it's moving in a circle. But the speed at which this is moving is a constant. So that's what and the radius is a constant. So the speed is a constant, and the radius is the magnitude of the radius is a constant. All right. So. So we want to study this kind of motion, and if you're in a car and you go around a turn, you're doing this. Maybe only for part of a circle, but like your car's coming this way, and then you go and you turn that way. You're moving in a circle. Now let's think about what we mean by acceleration. If you're sitting in a car. There's the ground. Here's the new Roadster 2. All right. And you want to accelerate this way. Well, what is that acceleration doing? Well, the car is going to go faster and faster and faster in to the right. Right? The velocity vector was smaller, but then the velocity vector gets bigger and bigger and bigger and bigger. You're speeding up. So what are we doing when we speed up? Okay. Well, we're acceleration, we said, was a change in velocity over a change in time. So what are we changing about the velocity vector of this car as it moves? Well, we're changing its length. Now imagine a car that's going really fast. Okay, it's going really fast, but then we're going to start slowing down, slowing down, slowing down, slowing down. Stop. Well, now the acceleration is in this direction. We call this, slowing down. But again, all we're doing is changing the length of the velocity vector, right? We're changing its magnitude. We're reducing its magnitude. Okay, we talked a lot about this earlier in the school year. And you can feel this. If you're zoom in. You can feel like if you're in a car and you speed up, what do you feel? You feel like you're getting pushed back in the chair. Or in your seat, right? Not your chair. You have a chair in a car. You're getting pushed back in your car seat. Why? Well, because your body has inertia and it wants to keep doing what it's doing. But if you're going to go faster and faster, the seat has to push you forward, and it makes you feel like you're getting thrown back. But you're not getting thrown back. You're getting pushed forward. Does that make sense? And then when you brake, well, your body's moving really, really fast. So So something has to, push you backwards, against your direction of motion. So you feel like you're getting thrown forward, but you're not really getting thrown forward, you're getting pulled backwards. It makes you feel like you're getting thrown forward. Does that make sense? Okay. And both of these kinds of acceleration, we are changing the velocity by increasing its speed or decreasing its speed. But what if you're going in a circle? And we're going in uniform circular motion. That is, my speed isn't changing. If this is my velocity vector right here, well, I would have the same velocity here. I would have the same speed here. I would have the same speed here. No matter where I am, I tried to draw all these the same length. I don't think I succeeded, but I tried. Okay. So you're going the same speed all the way around. But you've been in a car, right, where you take a, you ever put a donut down in a park? I never have. I would never do that. You know what a donut is? I mean, beyond just like going to the Judy's Donuts. Yeah, I mean, people do that. They go around and they put a skid mark on the ground. Don't do that. It's not very safe. It really eats up your tires too. But anyway, if you go around and turn, what do you feel? Let's say we're going around we're looking down, and here's your car. And your car is going around this circle. What do you feel? You feel as if you're getting thrown out the side of the car, don't you? But remember, what you feel is kind of backwards. What's actually happening is that you're getting pushed towards the center of the circle that you're driving around. Now, be careful. If you're the driver, I want you focusing on the road. But if you're a passenger, I want you to pay attention to what you feel when you're driving around and you go around a turn. I want you to feel that that's a different kind of acceleration. Acceleration, right, is defined to be the rate at which I change velocity. But look, I can change velocity by increasing its magnitude, decreasing its magnitude, or what am I doing to the velocity vector as I go around a circle? I'm changing its direction. And that requires an acceleration. By the way, we define acceleration in physics. Acceleration is defined to be the rate at which I'm changing. Velocity. Well, you can see that the velocity vector is getting changed as time goes by, pretty much at a steady rate. And if you go around a turn, or if you're on a Ferris wheel, or not a Ferris wheel, merry-go-round or something like that, it's making you go in a circle, you can experience that acceleration that changes your direction. And we have a name for this acceleration that where the acceleration, instead of speeding up or slowing down, it's changing direction. Changing direction. We call it centripetal acceleration. That's the acceleration that changes your direction. It doesn't change your speed. So what you feel is sideways to your motion, right? If you're going forward, when you go around a turn at constant speed, you feel a sideways pull on you. And that pull is trying to force you to go. It feels like you're getting thrown out the side, but you're not getting thrown out the side. You're getting pushed towards the middle of that circle. And that's what centripetal means. The word centripetal means center-seeking. It's pointed towards the center. It's a fancy way of saying towards the center of a circle. Centripetal. towards the center of a circle. Changing direction. Okay, well, I think that you have experienced this before. Like, have you ever taken a turn too fast? You know, and you whoa, and everything on your dashboard and in your car just slides off to the side, and you feel like you're going to lose control, and it's kind of scary. All right. So obviously, the centripetal acceleration is related to my speed, how fast I'm going. Right? If I'm going really fast and I go around a turn, whoa, I really am going to need a lot of centripetal acceleration. I feel a big, pull on me. We'll talk about centripetal force here in a second. But also, you ever see people, they're going to turn right, but before they turn right, they turn left a little bit before they turn right? You ever do that? Why are you doing that? Yeah. Yeah, the bigger the circle, the less stuff will fly across your car, right? So, and that's the radius of turn. You're trying to increase the radius of the turn. So, if you take a turn really, really sharp, a really sharp turn, you get a lot of acceleration, right? So it seems like there's an inverse relationship between the smaller the radius at a given speed, the more centripetal acceleration you're going to feel. And we're going to actually prove this. And here's the equation right here that we're going to prove. We're going to say that the centripetal acceleration, the center-seeking acceleration, this acceleration that changes the direction of our motion, is related to the speed squared. If you double the speed going around a turn, you will quadruple the amount of acceleration you need to go around that turn at that speed. Quadruple it. That's why when you get to a hairpin turn and they say you better drive 20 miles per hour around that hairpin turn, you better drive 20 miles an hour. If you go around it at 60 miles an hour, you are going off the road. Because if you go twice as fast as you should, you're gonna need 4 times as much friction to get you around that turn. We'll talk about friction next time. And that's why, like on the freeway, most people are going 75 miles an hour and there's a turn, you notice they're really gradual turns, right? No sharp turns on the freeway, because sharp turns on the freeway will get everybody killed. All right. So what we're going to do is we're going to show why this is true. It's intuitively true. You already kind of intuitively understand that the faster you go, the greater the acceleration, and that the sharper the turn, the smaller the radius of your turn, the greater the acceleration. And now we're going to prove why. Now this is a proof. You do not need to memorize this proof. But I want you to know that I'm not just pulling this out of thin air. Okay. So let's take a look at an object that's moving in a circle. We're looking down on it. Here's my little object. And it has a velocity vector. And it has a position vector. And what I'm going to do is I'm going to put my origin right there at the center of that circle. And this is the initial velocity vector. Now this is a vector too, this R. This is a vector. Zoom in, I drew it too small. This is a position vector. It's a vector, and this is a vector. And so this is where it is initially. So let's say you look at it, and then you let a small time interval go by, maybe a half a second or something, and then you notice that the object is over here. And here's the velocity vector here. We'll call this the final velocity, and here's the position vector, the final position vector. Now, one thing you need to understand is that if you're going on a path, along a path, you see that your velocity vector is always tangential to your path. I mean, your path might be turning, and so you have to turn that velocity vector with it. Now let's suppose that I call this theta. This is the angle theta. Now what I'm going to do is this. I'm going to say the change in my position, like obviously I started here and I went here. So my change in position is equal to R final minus R initial. And then I can rearrange this and say, okay, look, R final equals R initial plus my change in R. This is a vector equation, and I'm going to redraw it. I'm going to draw it right below here. So I'm going to say, okay, here's R initial, and then here's R final, and then here's delta R. And we said that this final vector here, this final position vector here, is equal to the initial vector here plus delta R. So there's delta R. Now if I were to draw delta R up here, the object started here and went over here. So there's my delta R on that picture. Now, you see that, whenever you add vectors together, you make a triangle. And do you see that R initial and R final have the same length, right? I mean, it's just the radius of the circle. The radius of a circle is a constant. So what kind of triangle has two legs that are the same length? Yeah, that's called an isosceles triangle, right? And here's now, but I also changed my velocity, right? And this is equal to V final minus V initial. Now notice I didn't change speed, but I did change my velocity, and we're going to see it right here. I'm going to do the same thing. I'm going to say that the final velocity, that is this vector right here, is equal to my initial velocity vector plus my change in velocity. Now, I can't draw a delta V very easily up here in this picture, but I'm just going to draw it over here. So I'm going to take V initial, and I'm going to take V final, and I'm going to put it right there. And so the delta V, the change in velocity, is my initial velocity vector plus delta V equals that. Okay? Now everybody take a look at that. Let's pause for a minute and look at this and make sure you understand what I did. And if you don't, ask a question. I just said, look, here, this vector, if I took this initial vector and I put it right there, then delta V would be like that. Okay. Well, here's what I want you to see. Do you see that that if R is rotated through theta, if R is rotated through theta, then V is rotated through theta as well. let's see, in a circle like this, the position vector and the velocity vector are always perpendicular to each other if you're going around a circle. So if my pencil here represents my velocity vector and my finger here represents the position vector, and I rotate this through theta, well, this is getting rotated too. It's getting translated, it's moving, but if I bring it back, what I'm trying to say is that this angle theta here will also be here. Okay? Now, so if you can accept that the velocity vector gets rotated by the same angle as the position vector gets rotated, well, and my speed is the same. And what is speed? Speed is the magnitude of this velocity vector I've drawn. Well, then, if these two are the same, it makes a triangle. What kind of triangle is that? It's an isosceles triangle just like this one. These two triangles are both isosceles, and they both have the same angle here, and therefore all their angles are the same. What do we call two triangles where all the angles are the same? They're not the same. They're not congruent, but they are similar. And similar triangles, as you learned in geometry, are proportional. So here's what I'm going to do. I'm going to say delta R is to R. And it doesn't matter if you use R initial or R final, because I'm just looking at magnitudes here. Is the same as delta V is to V. Doesn't that make sense? Yeah, I mean, this is a proof, and so, it has been shown in previous proofs that isosceles triangles are proportional. This is to this as this is to this. And you can do any kind of proportion you want and it'll work. But this is the one I want. Okay. Now I'm going to do something that algebra lets me do. I'm going to divide both sides by the time interval it took to go from here to here. Why? Because I can. As long as I do to one side what I do the other, it's legal. Now, I'm going to rearrange this a little bit. I'm going to say this is 1 over R times delta R over delta T equals delta V over delta T times 1 over V. All I did was switch these two and switch these two. Now I'm going to do something a little bit advanced for AP Physics 1. And if you don't like this part of it, that's fine. Don't worry about it. I want this to be, for this whole expression, we're going to take the limit and let delta t go to 0. Now what I'm saying here is that we're going to let this thing right here, this ratio of delta r over delta t is going to shrink, and both the numerator and denominator are going to shrink to tinier and tinier numbers, and that's called taking a derivative. But actually, if you're not in calculus yet, don't worry about it. What is delta r over delta t? What do we call delta r over? This is a change in position over change in time. Well, that's delta r over delta t is my speed. So I have 1 over r. And if you let the limit as delta t go to 0, this is like taking the slope of the tangent line we were talking about before. It's our instantaneous velocity. In this case, our instantaneous speed. Now, delta v over delta t. We have a name for delta v over delta t. What is that? Acceleration. And if we let the limit as delta t go to 0, that becomes our instantaneous acceleration times 1 over v. Now this is the acceleration I want to find. So I'm going to solve for it by multiplying both sides. So a equals, I'm going to multiply it both sides by v, and I get v squared over r. Woohoo! This is what I wanted to show you. So this is when we're moving in a circle. Let me zoom all the way out here so we can see the whole thing. When we're moving in a circle, we are changing our velocity vector. We're not changing our speed, but we're changing our velocity vector. And you need an acceleration to do that. And we went through this little proof showing that the acceleration, it depends on the speed, squared, velocity squared, divided by the radius. So the bigger your radius, the smaller your acceleration. That's why you take nice wide turns if you want a nice gentle, you don't want all your stuff on your dashboard to shove off to the side. You take a nice wide turn. Or if you go too fast, it really makes a big difference. If you go twice as fast, you're going to have 4 times the acceleration required to go around that turn. So this is centripetal acceleration, and it is the acceleration that changes the direction. Now, what direction is it changing it? Well, notice that this velocity vector is getting, well, if you're moving in a circle, let me redraw it. And I'll draw, little different places along the circle. This could be a car. You're looking down on a car, going around in a circle. And here are the velocity vectors. Well, here are your acceleration vectors. Your acceleration is always pointed towards the center of the circle. That's why you feel like you're being thrown out the side of the car, but you're not. You're being pulled towards the center of that circle. And that acceleration is called centripetal acceleration. Now, what causes a centripetal acceleration? A centripetal force. Well, we know that the net force is equal to mass times acceleration. Well, if I'm moving in a circle, look, if you're riding in a car like this, and it's this car's going in a circle, what happens if you hit a patch of ice or something and there's no more friction between your tires and the road? What are you going to do? You're just going to go tangential off like that. Because you don't have a net force on your car anymore. So the velocity of your car isn't going to change anymore. So if you're going like this, you're just going to keep going like that. So the net force that causes a centripetal acceleration, if you're moving in a uniform circular motion, that acceleration is v squared over r. So that's your net force. So if you have an object that's moving in a circle and there's some force acting on it from the outside, and we call that force, now it could be the force of friction if it's a car going around a circle. It could be gravity if it's a satellite moving around the Earth. It's the force of gravity. We're going to study that later. if I have a mass on a string and I'm whirling it around my head, it's the tension force in the string. And all of those will cause this net force that will cause the object to move in a circle. V squared over r. So I think we covered it. Make sure you understand the definition of acceleration, what a centripetal acceleration does, and you just multiply that centripetal acceleration by the mass of the object, and now you have the centripetal force acting on the object. A centripetal force is a net force, all right, in uniform circular motion. Okay, and here are the equations that you should add to your equation list. Any questions? Okay. Well, that is all.